Hello everyone, welcome back to our last problem. And boy, is it a doozy. Is it a doozy because it's hard? Well, not really. It's not actually all that much different than our previous problems. The big thing though is that I am giving you something new to do. My pen continues to want to foil my plans. There we go. Okay. I am giving you not just a cross section, no, but you have to actually solve a problem. What's the bending moment going to be? Ooh, yes, you're actually having to look at this and figure out what it's going to be inside this section, because this is probably where we care about it. So, what do we want to find? We want to find the maximum tension and compression bending stresses produced in segment BC of the beam. Okay, so as always, you go off, you try it, see how it works. Ask the squirrel. The squirrel I'm sure is going to be helpful. If you haven't watched the previous videos, it's very confusing why I'm talking about a squirrel, but that's okay. I'm just gonna leave it there. And in a few seconds, we'll try it all together. So go try it, see how it goes. So 3, 2, 1, you're back, and let's see how it went. So what's our first step going to be? Well, we gotta find the central location. We got our nice little sort of U-shaped beam, but now we gotta figure out where that centroid is. So for the left and the right stem, the area is going to be 0.75 inches and the bottom flange is going to be 0.5 inches. The distance to the centroid of the left and the right is going to be 1.5 inches. If we go back a little bit, we see they are 3 inches tall and we're breaking it up like this. Breaking it up like this, which means I don't have to worry about this bottom flange being on top. So for a rectangle, it's right at the centroid. Right at the center, so I should say. Okay, for the bottom one, it's 0.25 inches tall, and so it's going to be half that height. And then we multiply everything together and plug it into our equation to get that the centroid is 1.156 inches from the bottom. So it's very, very important that you make sure you know where you're measuring from. Okay, second thing is, what is our moment of inertia? What's our moment of inertia going to be? Well, we calculate it using our basic formula, which is that 1/12 base height cubed to begin with. But that's only about their own centroids, and that only works if their centroid is in line with the actual centroid, the centroid of the overall section, which for all these, that's not the case. So I figure out how far away they are. The positives and negatives here don't actually matter. That won't always be the case, but for right here, it doesn't matter. And we plug that into our d squared a equation to get the correction to the moment of inertia about their centroid, to figure out what the moment of inertia about the actual centroid would be. So with that, I get the total moment of inertia for this in inches to the fourth. Okay, I have the centroid, I have the moment of inertia. I think that we can almost solve things. Now I've got one more thing I have to do, which is I've got to figure out what the bending moment is in this section. We know for pure bending that our shear stress goes to 0. That's normal. So right here at this point, we have two reaction forces of 400 pounds at either end, and that gets canceled out by these 400 pounds here. However, the bending moment that occurred before that point doesn't go away. It doesn't go away in this section, and it disappears afterwards. So, with that in mind, what we can see is that we would have a bending moment of 400 times 1.5. 400 times 1.5. That would be our bending moment right there. So that would come out to be 600 pound-foot. 600 pound-foot. Okay, so we have the central location, we have our moment of inertia, and we have the 600 pound-foot. So what we have to realize then is if we're trying to find tension or compression, well, for a positive bending moment, this is positive, we're going to have compression above and tension below. So y will be negative to get our tension. It'll be negative 1.1563, that's just the distance to the bottom surface. And from our flexure formula, which is the moment, bending moment times the distance to that point from our centroid, all over the moment of inertia, and making sure to convert from foot to inches, and I'll get 4,533 psi, and that'll be in tension. Then I go to the opposite end. I go to the opposite end, which it was 3 inches tall. And so 3 minus 1.1563 is equal to this number right here. I plug it into my flexure formula once more. And what do I see here? What I see is I've got my bending moment. I have my distance to the point I care about, which in this case is at the top of my U shape. So from that point right here, all the way to there, that's where I'm calculating my bending stress. All over the moment of inertia around the z-axis. I get 7,230 psi. And that would be in compression. So that is it. That is it. Also, if you notice, tension is always considered positive, compression is always considered negative, and it all works out like it should. So if you're very careful about your signs, this will all work out and you'll get a positive number for the tension stresses and a negative number for compression. So I believe that's everything. It is. So thank you all for listening. I hope this helps you. And I'll see you all next time as we learn a little bit more about calculating these internal bending stresses. Have a wonderful day. Bye-bye.